Tonight, we're exploring the most spectacular death scenes in the cosmos. The universe's most massive stars have a completely different retirement plan. These stellar giants don't just fade away quietly. They explode with the force of billions of suns. Single stars that temporarily outshine entire galaxies. And here's something that might surprise you. The iron flowing through your bloodstream right now was forged inside one of these stellar explosions. The calcium strengthening your bones, even the gold in your jewelry. Every heavy element in your body is stellar ashes, remnants of ancient cosmic violence scattered across space billions of years ago. Tonight, you'll discover how these incredible explosions work, why they happen, and why they're absolutely essential for everything we know about life and planets. So settle in. Before we begin, leave a quick note in the comments, where you're listening from, or one thought you're carrying tonight. I read them, and they genuinely help shape future journeys. If you'd like more nights like this, subscribe, only if you enjoy these late-night journeys. Now let's begin. Ancient people looked up and saw eternal lights. Stars were permanent decorations. They twinkled politely and minded their own business. Even brilliant astronomers assumed stellar death meant slowly dimming over millions of years, like cosmic night lights gradually running out of batteries. February 24, 1987 completely shattered this assumption. Astronomers aimed their telescopes skyward that night. A dying star was throwing the universe's most spectacular tantrum. This stellar explosion blazed with the power of 200 million suns. It happened 160,000 light-years away in a neighboring galaxy, yet it became visible to naked eyes on Earth. Talk about making an entrance from the cheap seats. Picture our Milky Way galaxy. It contains 200 billion stars. Each one burns as a massive nuclear furnace for billions of years. Now imagine a single stellar explosion competing with all of them combined. That's exactly what Supernova 1987A accomplished. It reached peak brightness equivalent to 5 billion suns. Supernova become cosmic lighthouses detectable across billions of light years. Astronomers spot these stellar explosions in galaxies so distant their light started traveling when the universe was half its current age. A single dying star can outshine its entire host galaxy for months. It's the ultimate stellar attention grab. One star is essentially screaming, "Look at me." Across the entire cosmos, the physics behind this cosmic showboating defies human understanding. In less than 1 second, the exploding core converts 10% of the star's mass directly into pure energy. Einstein's E equals mc squared cranked up to 11. One supernova releases more power in seconds than our sun will produce in 10 billion years. Our sun seems incredibly powerful. It produces 400 trillion watts continuously. This energy drives Earth's weather, powers every plant on the planet, sustains all life for billions of years. Most people assume nothing could possibly generate more energy than our reliable stellar furnace. This assumption would prove hilariously inadequate. Supernova completely demolished the cosmic energy competition. When a massive star's core collapses, it releases about 10 to the 44 joules in the initial explosion. That's more than 1,000 times our sun's complete 10 billion year energy output, all crammed into a few heartbeats. It's like fitting Niagara Falls through a drinking straw, then setting it on fire. This energy creates the most extreme conditions anywhere in the natural universe. Core temperatures hit 100 billion degrees Celsius. That's 6,000 times hotter than our sun's interior. At these temperatures, atomic nuclei don't just collide. They engage in the cosmic equivalent of demolition derby. They forge elements heavier than iron through pure nuclear violence. But here's where things get genuinely weird. We only see a tiny fraction of this cosmic fury. Most of the explosion's power emerges as ghostly particles called neutrinos. These invisible messengers are the universe's ultimate introverts. They barely interact with anything. They race through solid rock like it's air, through entire planets like they're soup bubbles. During Supernova 1987A, underground detectors caught these particles arriving from another galaxy. Picture that, invisible messengers traveling 160,000 years to knock on our detectors. The first time humans directly intercepted a stellar death certificate from across the cosmos. The violence shapes everything about the aftermath. Blast waves race outward at 30,000 kilometers per second. That's fast enough to lap Earth in 90 seconds. This expanding shockwave turns surrounding space into a cosmic microwave. It heats gas to millions of degrees, accelerates stellar debris to near light speed. What if you wanted to catch a supernova in our galaxy? You might want to adjust your expectations about timing. These stellar explosions operate on a cosmic schedule that makes human patience look comically inadequate. In our entire Milky Way galaxy, supernovae occur roughly 2 to 3 times per century. That means the last one visible from Earth happened over 400 years ago. But here's where the cosmic perspective gets fascinating. Our galaxy represents just one neighborhood in an incomprehensibly vast universe. When astronomers expanded their view beyond our local stellar community, they discovered something remarkable about the true pace of stellar explosions. Somewhere in the observable universe, a massive star explodes approximately once every second. Right now, as you listen to this sentence, another star just detonated in a galaxy billions of light years away. By the time you finish this paragraph, 3 more stellar giants will have completed their final transformation. The universe operates a continuous fireworks display that never stops, never pauses, never takes a break. This relentless pace of stellar death might seem violent or disturbing, but it represents one of the cosmos's most essential processes. Each explosion enriches surrounding space with elements heavier than iron. Gold, platinum, uranium, rare earth elements, all forged in stellar cores during those final explosive seconds. Without this steady rhythm of stellar death, the universe would remain a sterile collection of hydrogen and helium gas. The numbers reveal just how industrious the universe has been at stellar destruction. Astronomers estimate roughly 3 billion supernovae have exploded in the observable universe since the Big Bang. That's 3 billion stellar factories converting simple hydrogen into complex elements. Every second of cosmic time, another star somewhere completes this essential transformation. February 23, 1987 started as an ordinary night for astronomers in the southern hemisphere. Clear skies, routine observations. Nothing suggested they were about to witness the most significant stellar explosion visible from Earth in over 400 years. Then something extraordinary happened that would revolutionize our understanding of how supernovae actually work. A Canadian astronomer named Ian Shelton was developing photographs at a Chilean observatory. He noticed something that shouldn't have been there. A bright new star had appeared in the Large Magellanic Cloud, our neighboring galaxy 160,000 light-years away. But this wasn't just any new star. It was blazing with the brightness of 20 million suns and getting brighter every hour. Within days, supernova 19A7A became visible to naked eyes despite occurring in another galaxy entirely. Think about that distance for a moment. Light from this explosion traveled for 160,000 years across empty space before reaching Earth. Yet it arrived bright enough to see without any telescope at all. You could walk outside on any clear night and spot it easily in the southern sky. A stellar explosion in another galaxy became part of our local night sky experience. This visibility represented something genuinely extraordinary in astronomical terms. Most supernova remain invisible to naked eye observation even when they occur within our own galaxy. The vast majority require powerful telescopes to detect across cosmic distances. But SN 1987A generated so much energy that it overcame 160,000 light-years of cosmic distance. The explosion provided the first opportunity for modern instruments to study a nearby supernova in real time. Neutrino detectors buried underground recorded the arrival of ghostly particles from the stellar core collapse. Space telescopes monitored the expanding blast wave as it plowed through surrounding gas clouds. For the first time, astronomers could watch the complete supernova process unfold with cutting-edge scientific instruments. Every time you breathe, you're inhaling atoms forged in the heart of exploding stars. The iron flowing through your bloodstream right now was created during violent stellar explosions. These explosions happened billions of years before Earth even existed. Your body contains roughly 4 grams of iron, all of its stellar ashes scattered across space by ancient supernovae. You're literally made of star dust, but not in some poetic, metaphorical sense. In the most direct, physical way possible. Here's what makes this cosmic connection even more remarkable. The calcium strengthening your bones and teeth was also forged in stellar cores during those final explosive moments. So was the phosphorus in your DNA, the sulfur in your proteins, the magnesium that helps your muscles contract. These elements don't exist naturally anywhere else in the universe. They can only be created through the nuclear violence that occurs when massive stars explode. Before the first generation of massive stars died and exploded, the universe contained almost nothing but hydrogen and helium. No carbon to build complex molecules, no oxygen to form water, no silicon to create rocky planets. The early cosmos was a sterile collection of the 2 lightest elements floating in empty space. Supernovae don't just create heavy elements. They distribute them across space in the most dramatic way possible. The blast waves from stellar explosions accelerate stellar debris to thousands of kilometers per second. These enriched materials race outward from the explosion site. They mix with surrounding gas clouds over millions of years. Your body represents the end result of billions of years of stellar recycling. Ancient stars lived, died, and exploded to create the elements that eventually became Earth. Then geological processes concentrated these stellar elements into the chemistry of life. Every breath, every heartbeat, every thought depends on atoms that were forged in the cores of dying stars billions of years ago. You're not just connected to the cosmos. You're composed entirely of cosmic leftovers from the universe's most violent stellar explosions. Not every star gets to go out with a bang. The universe operates a surprisingly exclusive membership policy when it comes to spectacular stellar explosions. Think of it as the cosmic equivalent of an elite country club, one with impossibly high membership fees. The admission standard is brutally simple. Your star must weigh at least 8 times more than our Sun. That's roughly 1.6 million times the mass of Earth packed into a single stellar furnace. Any star lighter than this cosmic weight limit gets rejected immediately. No exceptions. No appeals. Our Sun fails this membership test spectacularly. At exactly 1 solar mass, it weighs about 8 times too little to qualify for supernova status. When our Sun eventually dies in about 5 billion years, it will expand into a red giant. Then it will gently shed its outer layers into space. Finally, it will settle into white dwarf retirement about the size of Earth. No explosion, no cosmic fireworks, just a quiet fade into stellar obscurity. But here's where the Cosmic Club gets genuinely exclusive. Even among stars massive enough to qualify for membership, the universe has created different tiers of explosive privilege. Stars between 8 and 25 solar masses get basic supernova membership. They explode once and leave behind neutron star remnants. Stars above 25 solar masses earn premium membership status. They create the most energetic explosions. They can leave behind black holes as their final monuments. The most elite members weigh over 100 times our Sun's mass. These stellar behemoths burn so intensely they explode as hypernovae. They release hundreds of times more energy than ordinary supernova. They represent the universe's most exclusive explosive club. Only the most massive stellar giants earn the right to participate in these ultimate cosmic demolition shows. The universe has a twisted sense of humor when it comes to stellar lifespans. You might assume that bigger stars live longer, like massive ancient trees surviving for thousands of years while smaller plants wither quickly. This assumption would be completely backwards. In stellar neighborhoods, size becomes a death sentence. Bigger stars die spectacularly young. A star 30 times more massive than our Sun burns through its nuclear fuel so violently that it only survives about 6 million years. That's roughly 1,000 times shorter than our Sun's expected 10 billion year lifespan. These stellar giants live like cosmic rock stars. They burn incredibly bright, they party intensely, and they die young in the most spectacular way possible. Why do massive stars commit such dramatic stellar suicide? The answer lies in their incredibly wasteful energy production habits. Bigger stars don't just burn fuel faster, they burn it with reckless abandon. The nuclear fusion in their cores operates at such extreme temperatures and pressures that they consume hydrogen reserves at absolutely ridiculous rates. Here's the cosmic mathematics of stellar death. Double a star's mass and it burns fuel roughly 8 times faster. Triple the mass and fuel consumption increases by 27 times. A star weighing 10 times more than our Sun consumes nuclear fuel 1,000 times more rapidly. It's like comparing a hybrid car's gas mileage to a jet engine's fuel consumption. Massive stars are essentially cosmic jets burning through stellar fuel reserves at unsustainable rates. This creates the universe's most counterintuitive relationship between size and longevity. Red dwarf stars weighing just 10% of our Sun's mass can burn steadily for over 1 trillion years. Meanwhile, blue supergiant stars burn so intensely they exhaust their nuclear reserves faster than most civilizations rise and fall. The cosmic lesson seems clear. Live fast, burn bright, explode spectacularly. Sometimes stellar explosions result from what astronomers politely call a binary system interaction. The reality involves something much more dramatic: cosmic cannibalism that ends with explosive indigestion. Picture two stars locked in orbital partnership for millions of years. One dies first and becomes a white dwarf, essentially a stellar corpse about the size of Earth but weighing as much as our Sun. Then things get interesting. The surviving companion star begins to age and expand into a red giant. As it grows larger, its outer layers drift closer to the hungry white dwarf partner. That's when the cosmic feeding frenzy begins. The white dwarf starts stealing material from its bloated companion through gravitational theft. Gas streams flow from the red giant onto the white dwarf's surface, like stellar spaghetti being slurped up by an incredibly dense cosmic monster. This stolen material accumulates on the white dwarf's surface. It creates an increasingly unstable situation. White dwarfs have a strict weight limit built into the physics of stellar remnants. They can't weigh more than 1.4 times our Sun's mass without catastrophic consequences. Astronomers call this the Chandrasekhar limit. When the white dwarf finally exceeds this cosmic weight limit, the result is immediate and devastating. The entire stellar remnant explodes in a runaway nuclear explosion. It completely destroys the white dwarf. Nothing remains except expanding gases racing outward at thousands of kilometers per second. This creates what astronomers call a Type 1a supernova, stellar death through cosmic overheating. These explosions are remarkably consistent because they always happen when white dwarfs reach the same critical mass. They explode with nearly identical energy output regardless of where they occur in the universe. This predictable brightness makes them excellent cosmic distance markers. The universe's most reliable exploding stars became humanity's most accurate cosmic measuring tools. About 6042 light-years from Earth sits one of the most famous stars in our night sky. Betelgeuse marks the shoulder of the constellation Orion. It's visible as a distinctive reddish point during winter evenings. Most people admire it as a pretty stellar decoration. Astronomers see something far more dramatic, a massive stellar time bomb that could detonate at any moment. Betelgeuse weighs 15 to 20 times more than our Sun. That places it comfortably within the Supernova membership club we discussed earlier. This red supergiant has already begun showing signs of advanced stellar aging. It varies unpredictably in brightness. Its outer layers pulsate and shed material into space. These are the cosmic equivalent of an aging heavyweight boxer showing signs of fatigue before the final knockout. When Betelgeuse finally explodes, it will become spectacularly visible from Earth despite being 642 light-years away. The supernova will reach peak brightness equivalent to a half-moon visible during broad daylight. You'll be able to spot it easily in the middle of a sunny afternoon. At night, it will cast shadows on the ground. It will remain visible for several months as the brightest star in our sky. But here's the cosmic uncertainty that keeps astronomers guessing. Stellar evolution models suggest Betelgeuse could explode tomorrow, next year, or not for another 100,000 years. Massive stars become increasingly unpredictable as they approach their final explosive moments. The explosion poses no direct threat to Earth at our comfortable distance. The radiation and particle blast would be too diffuse to cause significant atmospheric damage, but it would provide the astronomical event of several lifetimes. Imagine a new star suddenly appearing brighter than Venus, visible in broad daylight, lasting for months. Social media would explode almost as dramatically as the star itself. Humanity's first Instagram-ready supernova happening in our cosmic backyard. Our galaxy operates like a cosmic powder keg. It's loaded with roughly 50 massive stars that could explode as supernova within the next few million years. These stellar time bombs sit scattered throughout the Milky Way. They're quietly burning through their nuclear fuel reserves, while astronomers maintain a cosmic watch list of potential candidates. Some of these future supernovae hide in plain sight as familiar bright stars. Rigel, the brilliant blue star in Orion, weighs about 20 times our Sun's mass. It burns fuel so rapidly it can't survive much longer on cosmic timescales. Antares, the red supergiant heart of Scorpius, has grown so large it would engulf Mars's orbit if placed at our Sun's position. Both represent stellar celebrities approaching their explosive final acts. Others lurk in more exotic stellar partnerships. Eta Carina, located about 7,500 light-years away, consists of two massive stars locked in a death spiral. They periodically erupt with incredible violence. In the 1840s, this stellar system briefly became the second brightest star visible from Earth. It expelled material weighing several times our Sun's mass. Astronomers consider it one of the most likely supernova candidates in our galactic neighborhood. Wolf-Rayet stars represent another category of supernova candidates. These stars have already begun shedding their outer layers through stellar winds. The winds are so intense they blow material into space at thousands of kilometers per second. These exposed stellar cores burn at incredibly high temperatures. They create some of the most extreme conditions possible in stellar interiors. They're essentially naked stellar furnaces approaching explosive meltdown. What makes this cosmic situation both fascinating and humbling is the uncertainty involved. None of these stellar candidates come with cosmic countdown timers. Some might explode next week. Others could continue burning for millions of years. The universe maintains its own schedule for stellar destruction. It operates completely independently of human curiosity or convenience. Somewhere in our galaxy, the next supernova is building toward its explosive finale. We just don't know which star will provide our next cosmic light show, or when it will begin. Deep inside a massive star's core, nuclear fusion operates like the universe's most efficient energy factory. For millions of years, this stellar powerhouse converts lighter elements into heavier ones. It releases tremendous amounts of energy in the process. Hydrogen becomes helium. Helium fuses into carbon. Carbon transforms into oxygen. The stellar assembly line continues building increasingly heavy elements while keeping the star shining brilliantly. Then the star makes a fatal mistake. It starts producing iron-56. Iron represents the ultimate dead end in stellar nuclear chemistry. Unlike every element that came before, iron fusion doesn't release energy. Instead, it actually requires energy input to create even heavier elements. When a massive star's core begins churning out iron-56, it's essentially manufacturing its own poison. The stellar furnace that has been producing energy for millions of years suddenly becomes an energy consumer. This cosmic fuel crisis happens with shocking speed. The star spends roughly 600 years burning helium. It spends 600 years fusing carbon. It consumes oxygen for about 1 year. But the final phase of silicon burning that produces iron lasts only a few days. Then everything stops. The nuclear reactions that have been powering the star since its birth suddenly shut down completely, like a massive engine running out of gas in the middle of a cosmic highway. Once the stellar core contains roughly 1.5 solar masses worth of iron, nuclear fusion becomes impossible. The star has essentially built its own nuclear graveyard in its very center. Iron nuclei sit there like cosmic paperweights. They can't fuse any further without consuming more energy than they produce. The stellar factory that has been running continuously for millions of years experiences immediate and complete industrial shutdown. For the star's entire life, an epic battle has been raging inside its core. On one side stands nuclear fusion, generating tremendous outward pressure. It constantly tries to blow the star apart. On the other side lurks gravity, constantly attempting to crush the star into the smallest possible space. This cosmic wrestling match has been perfectly balanced for millions of years, until the fuel runs out. The moment iron production shuts down nuclear fusion, gravity immediately gains the upper hand. Without energy constantly pushing outward from the core, there's nothing left to support the enormous weight of the star's outer layers. Several solar masses of stellar material begin falling inward under their own gravitational attraction. The collapse begins gently at first. Then it accelerates with terrifying speed. Gravity doesn't mess around when it finally gets its chance. The stellar core that took millions of years to build gets crushed in less than 1 second. Material that was previously held apart by fierce nuclear pressure suddenly finds itself squeezed into an increasingly tiny space. The core's temperature skyrockets as gravitational compression converts the star's massive size into concentrated thermal energy. This isn't just ordinary compression. We're talking about crushing several solar masses of stellar material into a space smaller than a large city. The gravitational forces involved are so extreme they overcome every known physical resistance mechanism. Electron pressure fails first. Then atomic structure starts breaking down as nuclei get forced closer together than nature normally allows. The stellar core essentially experiences the cosmic equivalent of being squeezed in a vice operated by a gravitational giant. Every second of collapse makes the situation more extreme. Higher temperatures, greater pressures, denser material. The star that has been slowly burning fuel for millions of years suddenly experiences the most violent transformation possible. All in less time than it takes to blink. Gravity's patient campaign over millions of years finally achieves total victory in the span of a single heartbeat. As gravity crushes the stellar core, something extraordinary happens. It challenges our everyday understanding of how matter behaves. The core that originally measured several thousand kilometers across gets squeezed down to roughly 20 kilometers in diameter. That's like compressing the entire San Francisco Bay Area into a sphere the size of Manhattan. But the physics involved goes far beyond simple spatial compression. The core's density increases by factors that make normal compression look pathetic. Normal stellar material weighs about 1 gram per cubic centimeter. That's roughly the density of water. During collapse, the core density skyrockets to 500 trillion grams per cubic centimeter. That's approximately the density found inside atomic nuclei themselves. We're literally watching stellar material get compressed to the point where it resembles one giant atomic nucleus. At these incredible densities, normal atoms cease to exist. The electrons that usually orbit atomic nuclei get crushed directly into the protons. They form neutrons through a process that would be impossible under ordinary circumstances. Imagine taking all the empty space out of normal matter, then cramming the remaining particles together as tightly as physics allows. The stellar core transforms from ordinary matter into something resembling a massive ball of neutrons, packed together like cosmic sardines. This compression happens so rapidly that the collapsing stellar core doesn't have time to radiate away the enormous amounts of energy being generated. The temperature climbs to over 100 billion degrees Celsius. Gravitational potential energy converts into thermal energy faster than it can escape. The core becomes a nuclear inferno compressed into a space smaller than most cities. But here's where the physics gets truly bizarre. Even gravity has limits when it comes to crushing matter. At nuclear density, neutrons begin exerting what physicists call degeneracy pressure, a quantum mechanical resistance that prevents further compression. The stellar core that has been collapsing for nearly a second suddenly hits an immovable wall. The irresistible force of gravity finally meets the truly immovable object of quantum physics. Deep inside the collapsing stellar core, two of the universe's most fundamental forces prepare for their ultimate showdown. In the blue corner, weighing several solar masses, stands gravitational collapse. It's trying to squeeze the stellar core into infinite density. In the red corner, representing quantum mechanical resistance, neutron degeneracy pressure refuses to allow any further compression. Cosmic boxing match about to determine the star's fate operates at temperatures of 100 billion degrees. Neutron degeneracy pressure sounds technical, but it represents something beautifully simple. Neutrons, like all quantum particles, refuse to occupy the same space as their neighbors. At nuclear densities, neutrons get packed so tightly together they collectively resist any additional squeezing. It's the quantum equivalent of a crowded subway car. Passengers physically cannot squeeze any closer together, no matter how much external pressure gets applied. This resistance creates the most extreme standoff imaginable. Gravity continues trying to crush the core smaller. Neutron pressure pushes back with equal force. For roughly 1 millisecond, these opposing forces achieve perfect balance. The stellar core stops collapsing and sits motionless in a state of incredible tension, like a cosmic spring compressed to its absolute limit. The core exists in a state so extreme that normal physics barely applies. The neutron matter inside weighs roughly 500 trillion times more per cubic centimeter than water. The temperature exceeds anything found anywhere else in the current universe. The pressure surpasses conditions that existed during the first moments after the Big Bang. All of this contained within a sphere smaller than most metropolitan areas. But this standoff cannot last forever. Something has to give way in this cosmic wrestling match between quantum mechanics and gravity. If gravity wins, the core collapses further and forms a black hole. If neutron pressure proves stronger, the core rebounds like a compressed spring suddenly released. The entire future of the stellar explosion depends on which fundamental force emerges victorious. This millisecond battle fought under the most extreme conditions possible in nature. The universe is about to find out which force rules supreme when matter gets compressed to its absolute physical limits. After 1 millisecond of perfect balance, neutron degeneracy pressure finally wins its battle against gravitational collapse. The stellar core that has been compressed to nuclear density suddenly rebounds, like a cosmic basketball hitting an absolutely solid floor. This rebound happens so violently and rapidly that it creates the most energetic explosion possible in the natural universe. The rebounding core generates a shock wave that races outward at roughly 30,000 kilometers per second. This blast wave carries enough energy to completely disintegrate everything in its path. The iron core that took millions of years to build gets vaporized in microseconds. The silicon layer above it disappears almost instantly. Oxygen, carbon, helium. Every carefully constructed stellar layer gets obliterated as the shockwave races toward the star's surface. But here's where the explosion physics gets truly incredible. The shockwave doesn't just carry kinetic energy. It also transports enormous numbers of neutrinos, ghostly particles that barely interact with ordinary matter. These neutrinos carry away roughly 9% of the explosion's total energy. They stream outward through the collapsing stellar layers like invisible messengers announcing the core's violent demise. The shockwave takes several hours to fight its way through the star's outer layers. As it travels outward, it heats surrounding material to billions of degrees. It accelerates stellar debris to significant fractions of light speed. When it finally reaches the star's surface, the explosion becomes visible as the brilliant supernova light we observe from Earth. The cosmic rebound that began in 1 millisecond has transformed a single star into one of the universe's brightest objects. What makes this process even more remarkable is its incredible efficiency. The stellar core converts roughly 10% of its total mass directly into pure energy during the collapse and rebound sequence. This makes supernovae the most efficient energy reduction mechanism known in the universe. It far exceeds the efficiency of nuclear weapons, fusion reactors, or any other energy source humans have ever imagined. The death of a single massive star releases more energy in minutes than our sun will produce during its entire 10 billion year lifetime. Nature's most violent millisecond creates the cosmos's most spectacular and long-lasting light show. The stellar core's violent rebound launches what might be the universe's most destructive race against time. A shockwave begins its journey from the collapsed center. It carries enough energy to completely dismantle a star that has been stable for millions of years. This isn't just any ordinary explosion propagating through space. This is a cosmic demolition wave. It must travel roughly 700 million kilometers to reach the stellar surface. That's about 5 times the distance from Earth to the Sun. The shock wave moves with absolutely staggering speed. At 30,000 kilometers per second, it travels fast enough to circle Earth's entire equator in roughly 1.3 seconds. That's about 10% the speed of light. It makes this one of the fastest moving physical phenomena in the universe. To put this cosmic velocity in perspective, the shockwave could travel from New York to Los Angeles in about 0.1 second. It's essentially a wall of devastating energy racing through the star's interior, moving faster than human reflexes can even register. But this energy sprint faces enormous resistance as it plows through increasingly dense stellar layers. The shockwave that started with tremendous power gradually loses energy. It fights its way outward through thousands of kilometers of stellar material. It's like watching a cosmic bulldozer push through obstacles that get progressively more stubborn. The deeper layers offer less resistance, but the outer layers require increasingly heroic amounts of energy to accelerate and eject. The shockwave's journey through different stellar zones creates a cosmic relay race of destruction. In the inner core region, it blasts through in milliseconds. The silicon and oxygen layers require several seconds to completely disintegrate. The outer hydrogen envelope takes minutes or hours to fully accelerate to escape velocity. By the time the shock wave finally reaches the star's photosphere, it has been traveling for several hours. It has lost significant energy. Yet it still carries enough power to accelerate the star's outer layers to thousands of kilometers per second. It launches them permanently into space. During the stellar core collapse, something remarkable happens that most people never learn about in basic astronomy courses. The explosion produces roughly 10 to the 58 neutrinos. That's a 1 followed by 58 zeros. These ghostly particles represent the explosion's invisible workforce. They carry away 99% of the total energy, while remaining almost completely undetectable to normal matter. Neutrinos earn their reputation as the universe's ultimate introverts. They interact with matter so weakly that they can travel through the entire Earth as if it were empty space. During a supernova, these invisible messengers stream outward from the stellar core in numbers that make astronomical figures seem modest. In just 10 seconds, the exploding star produces more neutrinos than our Sun will create during its entire 10 billion-year lifetime. Here's what makes neutrino energy transport so extraordinary. While the visible light from a supernova takes hours to fight its way through the star's outer layers, neutrinos escape almost instantly. They don't get slowed down by stellar material. They don't get absorbed by dense gases. They don't get deflected by magnetic fields. They simply race straight outward at nearly the speed of light, like invisible cosmic express trains carrying tremendous amounts of energy. The neutrino flood provides crucial assistance to the struggling shock wave. Billions upon billions of these particles stream outward from the core. A tiny fraction of them interact with matter in the stellar layers above. Even though individual neutrinos rarely interact with anything, the sheer numbers involved mean that collective neutrino interactions deposit additional energy into the shock wave. It's like having an army of nearly invisible workers. Each carries a tiny amount of energy. Collectively, they provide just enough extra help to ensure the explosion succeeds. Without this ghostly neutrino assistance, many stellar explosions would fail completely. The shock wave would lose too much energy fighting through the star's outer layers. It would stall before reaching the surface. The neutrinos essentially provide the extra push needed to transform a failed stellar implosion into a successful cosmic explosion. When the shock wave finally reaches the star's outer layers, it creates the universe's most dramatic fountain display. The star's hydrogen envelope weighs several times our Sun's mass, but it's millions of times less dense than the core. It gets blasted outward at speeds that make rockets look pathetic. This stellar material races into space at roughly 10,000 kilometers per second, fast enough to travel from Earth to the Moon in less than 40 seconds. The ejected material doesn't just drift quietly into space like cosmic litter. This stellar debris becomes a high-speed projectile show that continues for thousands of years. The expanding shell of ejected material sweeps up surrounding interstellar gas and dust. It creates shock fronts that heat everything to millions of degrees. The result is a glowing bubble of superhot gas expanding through space, like a cosmic soap bubble made of stellar fire. Different elements get ejected at different speeds. This creates a complex layered structure in the expanding debris cloud. the heaviest elements forged in the star's core during its final moments, travel somewhat slower than the lighter elements from the outer layers. This creates a cosmic sorting effect where elements arrange themselves by weight as they race outward, like a stellar explosion playing cosmic billiards with atomic nuclei. The expanding supernova remnant continues growing for tens of thousands of years. It eventually reaches sizes of dozens of light-years across. Long after the initial explosion fades from view, this expanding shell of stellar debris remains detectable to telescopes. It continues plowing through space. The Crab Nebula, visible to amateur astronomers today, represents the still expanding debris from a stellar explosion. Chinese astronomers recorded it in 1054 AD. What makes this cosmic fountain even more remarkable is its role in enriching the surrounding galaxy. The ejected stellar material carries with it all the heavy elements forged during the star's lifetime, plus additional elements created during the explosion itself. This element-rich material eventually gets incorporated into future generations of stars and planets. Inside the exploding stellar inferno, temperatures reach 3 billion degrees Celsius. That's roughly 200 times hotter than our sun's core. At these extreme temperatures, nuclear physics operates in ways that are impossible under normal stellar conditions. The explosion essentially becomes a cosmic alchemy laboratory. It manufactures elements too heavy and rare to be created anywhere else in the universe. During the explosion's most violent moments, atomic nuclei collide with incredible energy. They overcome the strong nuclear force's resistance to creating very heavy elements: gold, platinum, uranium, rare earth elements. All of these get forged through nuclear processes so extreme they can only occur during stellar explosions. The star's final seconds produce more exotic heavy elements than it created during millions of years of normal nuclear burning. This cosmic alchemy operates through several different nuclear processes happening simultaneously. Some heavy elements form when iron nuclei rapidly capture dozens of neutrons in fractions of a second. This process is called rapid neutron capture. It's impossible under normal stellar conditions. Other elements get created when lighter nuclei collide and stick together through pure brute force. Powered by the incredible temperatures and pressures inside the explosion. The gold in your jewelry required this cosmic violence to exist. Every gold atom was forged inside a stellar explosion at temperatures and pressures that would instantly vaporize planets. The rare earth elements in your smartphone underwent nuclear alchemy so extreme it literally required the death of massive stars. These precious metals aren't just rare on Earth. They're rare throughout the entire universe because they can only be manufactured in stellar explosions. But here's the cosmic economics of heavy element production. Even these incredibly violent stellar explosions produce relatively small amounts of the heaviest elements. A typical supernova might create roughly 1 Earth's worth of gold during its entire explosive sequence. Considering that these explosions completely destroy stars weighing 20 times more than our Sun, heavy elements truly represent cosmic luxury items. The universe's most violent explosions become its most exclusive jewelry factories, operating at temperatures that make stellar cores look cool and comfortable. Some supernovae don't just explode. They also emit focused beams of gamma radiation so intense they could threaten life across interstellar distances. These gamma-ray bursts represent the universe's most powerful electromagnetic weapons. They're capable of delivering lethal doses of radiation to planets located over 1,000 light-years away from the explosion site. Gamma-ray bursts occur when certain massive stars collapse directly into black holes. They simultaneously launch high-speed jets of material along their rotation axis. These jets accelerate particles to nearly the speed of light. They create focused beams of the universe's most energetic radiation. The resulting gamma-ray emission can outshine the combined light of all other stars in the observable universe for several seconds. If a gamma-ray burst occurred within 1,000 light-years of Earth, the results would be catastrophic for life on our planet. That would be especially true if it pointed in our direction. The intense radiation would strip away much of our ozone layer within seconds. This would expose Earth's surface to deadly ultraviolet radiation from our Sun. The initial gamma-ray pulse would be followed by months or years of increased cosmic radiation as our damaged atmosphere struggled to recover. Scientists estimate that gamma-ray bursts might be responsible for some of Earth's ancient mass extinction events. These cosmic death rays could explain sudden biodiversity collapses that occurred without obvious terrestrial causes. The universe occasionally produces stellar explosions so violent they can sterilize entire regions of galaxies. They create cosmic dead zones where complex life becomes temporarily impossible. Fortunately, gamma-ray bursts are extremely rare events. They require very specific stellar conditions to occur. Most supernovae explode more or less spherically and don't produce these focused death rays. But the existence of these cosmic laser weapons reminds us that the universe can be a genuinely dangerous place for life. The same stellar explosions create the heavy elements necessary for rocky planets. They also have the potential to sterilize those planets from distances of hundreds of light years. Space remains a cosmic shooting gallery where the wrong kind of stellar explosion could end civilizations across multiple star systems. After a supernova explosion finishes destroying a massive star, something remarkable happens to the leftover stellar core. The neutrons that successfully resisted gravitational collapse during the explosion don't just disappear. Instead, they form one of the universe's most bizarre objects, a neutron star that represents the ultimate achievement in cosmic weight loss and compression. Imagine taking our entire Sun, which weighs roughly 2 million trillion kilograms, and squeezing it down to the size of Seoul. That's approximately 20 kilometers across, small enough to fit comfortably within most metropolitan areas. This isn't just impressive compression. This is physics taken to such extremes that a single teaspoon of neutron star material would weigh about 1 billion tons on Earth. That's roughly the mass of Mount Everest compressed into something you could hold in your hand. The neutron star achieves this incredible density through the most efficient packing method known in the universe. Normal atoms contain mostly empty space. If an atomic nucleus were the size of a marble, its electrons would orbit at distances equivalent to several football fields. Neutron stars eliminate all this wasted space by crushing protons and electrons together into neutrons. Then they pack these neutrons as tightly as quantum physics allows. The surface conditions on a neutron star make every extreme environment on Earth look comfortable. Surface gravity reaches 200 billion times stronger than Earth's gravity. If you could somehow stand on a neutron star's surface, you would instantly weigh roughly the same as Mount Everest. The magnetic field's strength exceeds Earth's magnetic field by factors of trillions. It creates the strongest magnets anywhere in the known universe. But here's what makes neutron stars even more extraordinary. Despite being incredibly tiny by stellar standards, they contain more matter than our entire sun. The stellar core that survived the supernova explosion has been compressed to the absolute limit of what quantum physics permits. Any additional mass would overcome neutron degeneracy pressure entirely and create something even more exotic. A black hole. Neutron stars represent matter balanced exactly on the edge of the ultimate cosmic cliff. When a stellar explosion can't quite blow away all of the star's mass, the remaining core can exceed roughly 3 times our sun's weight. Then neutron degeneracy pressure finally admits defeat. The stellar remnant collapses beyond the neutron star limit. It creates something that challenges our basic understanding of reality. A region of space-time where gravity becomes so strong that not even light can travel fast enough to escape. Black holes don't just absorb light like cosmic vacuum cleaners. They fundamentally warp the fabric of space and time itself. Einstein's general relativity predicts that massive objects bend space-time around them. But black holes take this concept to its logical extreme. They create regions where space-time curves so dramatically that it essentially closes in on itself, forming cosmic trapdoors from which nothing can return. The boundary around a black hole represents the ultimate point of no return. Physicists call this the event horizon. Cross this invisible cosmic threshold, and every possible future path leads inexorably toward the black hole's center. Light, matter, energy, information. Everything that ventures too close gets permanently trapped. The universe's most efficient gravitational predators operate with perfect success rates. Nothing has ever escaped from inside a black hole's event horizon. The physics inside black holes becomes so extreme that our current understanding of reality breaks down completely. At the center lies what theorists call a gravitational singularity, a point where density becomes infinite and space-time curvature reaches mathematical impossibility. Normal physics simply stops working when matter gets compressed beyond neutron star densities. We're dealing with cosmic objects that exist beyond the boundaries of conventional science. Yet black holes do not just appear to destroy information. They also power some of the universe's most energetic phenomena. Material falling toward a black hole accelerates to significant fractions of light speed. It heats up to billions of degrees and emits incredible amounts of radiation. Some black holes launch jets of superheated particles across distances of thousands of light years. These cosmic engines convert gravitational energy into electromagnetic radiation with efficiencies that make nuclear fusion look wasteful. The universe's ultimate gravitational prisons also become its most powerful energy sources. Some neutron stars become the universe's most precise timekeepers by developing a cosmic case of extreme rotation. These rapidly spinning stellar remnants, called pulsars, rotate hundreds of times per second. They emit lighthouse-like beams of radiation from their magnetic poles. The resulting cosmic light show creates natural atomic clocks that keep better time than anything humans have ever built. The fastest known pulsar spins roughly 700 times per second. That's faster than the blades of a high-performance blender. Except we're talking about an object weighing more than our sun compressed into the size of a city. The rotational energy involved is so enormous that it would power Earth's electricity needs for billions of years. These stellar remnants have essentially become cosmic gyroscopes spinning with the momentum of entire stars. Pulsars achieve their incredible rotational stability through the same physics that makes figure skaters spin faster when they pull their arms inward. When the original massive star collapsed from a radius of millions of kilometers down to roughly 20 kilometers, conservation of angular momentum kicked in. It accelerated the rotation dramatically. It's like watching a cosmic ice skater perform the universe's most extreme pirouette, spinning up from once per day to hundreds of times per second. The lighthouse effect occurs because neutron stars possess incredibly strong magnetic fields, roughly 1 trillion times stronger than Earth's magnetic field. Charged particles get accelerated along these magnetic field lines. They create beams of radio waves that sweep through space like cosmic searchlights. When these beams happen to point toward Earth during each rotation, we detect regular pulses of radio emission with clockwork precision. This cosmic precision timing has practical applications that benefit human technology. Astronomers use pulsar timing to detect gravitational waves. They test Einstein's theories of relativity. They even search for planets orbiting neutron stars. The most stable pulsars keep time more accurately than atomic clocks. They lose less than 1 second every 10 million years. Nature has created cosmic timepieces that operate with precision exceeding the best human engineering. These spinning stellar remnants have become the universe's ultimate metronomes, keeping perfect time across galactic distances. Sometimes the universe decides that one neutron star isn't dramatic enough and arranges for 2 of them to engage in the ultimate cosmic collision. When neutron stars spiral into each other, they create explosions called kilonova. These explosions outshine ordinary supernovae and forge precious metals on scales that make terrestrial gold mining look pathetic. These neutron star mergers represent the universe's most exclusive precious metal factories. During the final moments before collision, the incredible gravitational forces literally tear both neutron stars apart. They eject neutron-rich material into space at significant fractions of light speed. This stellar debris undergoes rapid neutron capture processes that create heavy elements much more efficiently than any supernova explosion. A single kilonova explosion can produce an astonishing amount of gold. Enough gold in a thought experiment to make solid golden spheres the size of large asteroids. But kilonovae don't stop at gold production. They also manufacture platinum, uranium, rare earth elements, and virtually every stable element heavier than iron. These cosmic collisions operate as the universe's most productive heavy element assembly lines. The kilonova process happens incredibly rapidly. 2 neutron stars that have been spiraling toward each other for millions of years finally collide and merge in less than 1 second. During that brief moment, they release more energy than our sun will produce in its entire 10 billion year lifetime. The explosion creates a fireball that expands at thousands of kilometers per second. It gradually cools and glows with the characteristic light of newly forged heavy elements. What makes kilonovae even more remarkable is how rare these cosmic collisions are. Astronomers estimate that neutron star mergers are perhaps once every 10,000 years in a typical galaxy. Yet these incredibly infrequent events are responsible for creating most of the universe's gold, platinum, and other precious metals. The wedding ring on your finger contains gold atoms that were forged during one of these cosmic collisions billions of years ago. Every piece of jewelry represents stellar remnants from the universe's rarest and most violent cosmic accidents. The cosmos operates the ultimate luxury goods manufacturing system. It produces precious metals through stellar collisions so infrequent they make Earth's rarest gemstones look common. Massive stars that die through core collapse don't all follow identical explosion recipes. The universe operates something like a cosmic restaurant specializing in gravitational collapse. But it offers several different preparation methods depending on the stellar ingredients involved. These core collapse supernova, designated as Type II by astronomers, come in multiple flavors. They reflect the diverse ways massive stars can explode. Type IIp supernovae represent the classic gravitational collapse explosion. The P stands for plateau. It refers to how these stellar explosions maintain steady brightness for several months after reaching peak luminosity. These explosions occur when red supergiants with thick hydrogen envelopes collapse and explode. They create light curves that remain relatively flat for extended periods. They're essentially the universe's standard gravitational collapse recipe. Type IIL explosions offer a different preparation method. The L indicates linear. It describes how these supernovae fade more rapidly after peak brightness without the extended plateau phase. These occur when the exploding star has lost more of its hydrogen envelope before collapse. They create different light emission patterns. Same basic gravitational collapse process, but with modified stellar ingredients producing different observable results. Type IIb supernova push the envelope even further. These explosions happen when massive stars have lost most but not all of their hydrogen layers before core collapse. They initially appear similar to Type II explosions, but later develop characteristics resembling Type I supernova. This happens as the thin remaining hydrogen gets stripped away. They represent hybrid explosions that change personality partway through their explosive careers. Type Ib and Type Ic supernovae complete the core collapse family. These occur when massive stars completely lose their hydrogen envelopes before exploding, either through stellar winds or binary interactions. Type Ib explosions show helium in their spectra, while Type Ic have lost both hydrogen and helium layers. They prove that massive stars can explode through core collapse even after shedding most of their original stellar atmospheres. The gravitational collapse restaurant serves the same fundamental explosion process, but with dramatically different stellar seasoning and presentation styles. While massive stars explode through gravitational collapse, an entirely different category of stellar explosions operates through pure thermonuclear detonation. Type Ia supernovae occur when white dwarf stars exceed a critical mass limit and experience runaway nuclear fusion. This completely destroys the white dwarf. White dwarf stars are stellar remnants about the size of Earth, but weighing as much as our Sun. The cosmic weight limit governing these explosions is called the Chandrasekhar limit. It's named after the Indian physicist who calculated that white dwarf stars cannot exceed roughly 1.4 times our Sun's mass. Below this limit, white dwarfs remain stable stellar corpses supported by electron degeneracy pressure. Above this limit, quantum mechanical pressure fails completely. The white dwarf begins collapsing under its own gravity. But white dwarfs don't collapse quietly like massive stellar cores. Instead, the gravitational compression triggers runaway carbon fusion throughout the entire white dwarf simultaneously. The stellar remnant that has been sitting dormant for millions of years suddenly experiences explosive nuclear burning from its center to its surface. The entire white dwarf becomes a cosmic thermonuclear bomb that detonates in seconds. This thermonuclear explosion is fundamentally different from core collapse supernova. There's no neutron star or black hole left behind because the entire white dwarf gets completely incinerated. The explosion converts roughly half the white dwarf's mass into radioactive nickel-56. This subsequently decays into cobalt and iron. The remaining material gets blasted into space at speeds of thousands of kilometers per second. The key to Type 1a explosions lies in how white dwarfs approach the Chandrasekhar limit. Usually this happens through mass transfer in binary systems. The white dwarf gradually steals material from a companion star. As the white dwarf gains mass, it slowly approaches the critical threshold. When it finally exceeds 1.4 solar masses, the result is immediate and catastrophic. The universe's most precisely calibrated stellar bombs explode when quantum mechanics can no longer support stellar remnants. They have grown too massive for their own gravitational good. Type 1a supernovae have earned a reputation as the universe's most dependable cosmic lighthouses. Core collapse supernovae vary dramatically in brightness, depending on the exploding star's mass and structure. Type 1a explosions produce remarkably consistent peak luminosities. This standardized brightness makes them invaluable tools for measuring distances across cosmic scales. The consistency arises from the physics of thermonuclear explosion in white dwarf stars. Since all Type 1a supernovae occur when white dwarfs reach approximately the same critical mass, they all explode under nearly identical conditions. Same mass, same composition, and the same explosion mechanism produce very similar energy outputs. It's like having cosmic firecrackers that are manufactured to identical specifications. This standardization allows astronomers to use Type 1a supernovae as cosmic distance markers. Astronomers compare how bright these explosions appear from Earth to their known intrinsic brightness. Then they calculate how far away the host galaxy is. The dimmer the supernova appears, the greater the distance. It's the same principle used with ordinary light bulbs. If you know the bulb's true brightness, its apparent brightness tells you how far away it is. The remarkable consistency of Type 1a brightness enabled one of the most important astronomical discoveries of the past century. In the 1990s, astronomers used these standardized stellar explosions to measure the expansion rate of the universe across cosmic time. They discovered that cosmic expansion is actually accelerating. This acceleration is driven by mysterious dark energy that makes up roughly 70% of the universe. Type 1a supernovae essentially became humanity's cosmic measuring tape. They allow precise distance measurements to galaxies billions of light years away. These thermonuclear explosions provide the observational foundation for understanding how the universe has evolved over the past 13.8 billion years. The universe's most reliable stellar bombs became our most important tools for mapping the cosmos and discovering its ultimate fate. Cosmic destruction transformed into cosmic enlightenment through the precision of identical thermonuclear explosions. The universe operates separate assembly lines for heavy element production. Different types of supernova specialize in manufacturing different cosmic ingredients. Core collapse and thermonuclear explosions don't just differ in their explosive mechanisms. They also produce distinct elemental signatures that reflect their unique nuclear processing environments. Core collapse supernovae excel at producing what astronomers call alpha elements. These are elements whose nuclei contain whole numbers of helium-4 nuclei. They include oxygen, magnesium, silicon, sulfur, calcium, and titanium. The extreme conditions during massive star evolution and core collapse favor nuclear processes that build these elements through successive helium capture. Type II explosions essentially operate cosmic foundries specialized in producing the rock-forming elements that become planetary building blocks. Type Ia supernovae run completely different cosmic factories. These thermonuclear explosions specialize in producing iron peak elements, primarily iron, nickel, cobalt, and chromium. The runaway carbon fusion that destroys white dwarfs creates nuclear conditions ideal for building elements around iron-56. Iron-56 is the most stable atomic nucleus. Roughly half of all iron in the universe comes from Type Ia explosions, despite these being much rarer than core collapse supernova. The different production specialties create distinctive chemical fingerprints. Galaxies with active star formation show higher ratios of alpha elements to iron. This happens because massive stars evolve and explode quickly, enriching surrounding gas with oxygen and magnesium. Older galactic regions show higher iron content because Type Ia explosions occur later. They happen after white dwarf binary systems have had time to evolve and merge. This elemental specialization has profound implications for planet formation and life chemistry. The rocky planets in our solar system contain alpha elements from ancient core collapse supernova. They also contain iron peak elements from Type Ia explosions that occurred billions of years ago. Your body chemistry depends on both types of stellar explosions. It includes oxygen from massive star cores and iron from thermonuclear white dwarf destruction. The universe's two different supernova assembly lines combine their products to create the chemical complexity necessary for rocky worlds and biological systems. Different cosmic explosion recipes produced complementary ingredients that eventually became the periodic table of elements available for planetary chemistry. Astronomers once thought supernova fit neatly into core collapse and thermonuclear types. Then the universe revealed stellar explosions that refused to follow the established rules. Recent astronomical surveys have discovered multiple new categories of supernovae. They challenge fundamental assumptions about how stars can explode and die. Type Ia supernovae represent one of the most puzzling recent discoveries. These explosions appear similar to Type Ia events, but are significantly fainter. They show evidence that the white dwarf might survive the explosion partially intact. Instead of complete thermonuclear destruction, these failed Type Ia explosions might leave behind partially disrupted white dwarf remnants. The universe apparently operates white dwarf explosions with multiple power settings. Super-Chandrasekhar supernovae completely violate the mass limits that should govern white dwarf explosions. These exceptionally bright Type Ia events require white dwarf progenitors that somehow exceed 1.4 solar masses without exploding immediately. Astronomers are still debating how white dwarfs can grow beyond their theoretical weight limits and still produce thermonuclear explosions. These rule-breaking explosions suggest that stellar physics contains loopholes we haven't discovered yet. Calcium-rich transients add another layer of cosmic mystery. These faint explosions occur in galactic outskirts and produce unusually large amounts of calcium relative to other elements. They don't fit cleanly into either core collapse or thermonuclear categories. They might represent an entirely different explosion mechanism. The universe apparently operates additional stellar destruction assembly lines that astronomers are just beginning to recognize. Ultra-stripped supernova represent another recently discovered category where massive stars lose almost all their mass before exploding. This creates core collapse events that barely distinguish themselves from thermonuclear explosions. These stripped envelope explosions blur the traditional boundaries between different supernova types. They suggest that stellar evolution can follow more exotic pathways than previously imagined. Perhaps most remarkably, some of these new supernova categories might be powered by entirely different physics. Pair instability supernova were predicted theoretically, but only recently observed. They occur when the most massive stars experience runaway gamma-ray production. This destabilizes their cores before normal iron collapse occurs. The universe continues revealing new ways that stars can explode. It challenges astronomers to expand their understanding of stellar death. Cosmic rule breakers ensure that supernova science remains full of surprises and discoveries. They revolutionize our understanding of how stars can end their lives. Before the first generation of massive stars lived and died, the universe resembled a cosmic desert. It contained almost nothing but hydrogen and helium gas floating in empty space. No carbon to build complex molecules, no oxygen to create water, no silicon to form rocky planets. The early cosmos was essentially sterile, a vast collection of the two simplest elements with no possibility for interesting chemistry, geology, or biology. Supernovae transformed this cosmic wasteland into a universe capable of supporting complexity and life. Each stellar explosion operates like the ultimate seed dispersal system. It scatters heavy elements across millions of cubic light-years of space. The carbon in your DNA, oxygen in your breath, calcium in your bones, phosphorus in your cells. Many of the 26 elements essential for life were forged inside massive stars and distributed by supernova explosions. These stellar death events don't just create heavy elements. They launch them into space with enough energy to mix thoroughly with surrounding interstellar gas. Supernova shock waves accelerate newly forged elements to thousands of kilometers per second. This ensures they spread far beyond the explosion site. Without this violent dispersal mechanism, heavy elements would remain concentrated near their stellar birthplaces. They would never reach regions where new stars and planets form. The cosmic seeding process operates with remarkable efficiency. A typical supernova explosion enriches roughly 1,000 cubic light-years of surrounding space with heavy elements. Over billions of years and countless stellar explosions, supernova have gradually transformed the universe. They changed it from a hydrogen-helium wasteland into a cosmos rich with chemical diversity. Every region of space now contains the elemental ingredients necessary for rocky planet formation and complex chemistry. Your body represents the ultimate success story of this cosmic seeding campaign. The elements flowing through your bloodstream originated inside stellar cores that exploded billions of years before Earth existed. Supernova shock waves carried these elements across vast distances. They mixed them with primordial gas and delivered them to the region where our solar system eventually formed. You are literally composed of stellar ashes from the universe's most violent explosions. They were transformed into the chemistry of life through billions of years of cosmic evolution. The death of ancient massive stars became the foundation for every complex molecule in your body. Supernova don't just scatter elements into space, they also function as the universe's most effective construction crews. They trigger the formation of new stars through cosmic shock therapy. The blast waves from stellar explosions compress surrounding gas clouds with immense force. Gravity can finally overcome thermal pressure and build the next generation of stellar residents. Interstellar space contains vast regions of cold gas and dust that hover just barely below the density threshold needed for star formation. These molecular clouds drift through space for millions of years. They're too warm and diffuse to collapse under their own gravity. They need an external trigger to push them over the edge into active star formation. Supernova shock waves provide exactly the right kind of cosmic intervention. When a supernova blast wave encounters one of these dormant molecular clouds, it compresses the gas like a cosmic steamroller. The shock front increases local gas density by factors of 10 to 100. It creates conditions where gravity finally wins its battle against thermal pressure. Dense knots of gas begin collapsing under their own weight. They fragment into smaller clumps that eventually become individual stars. This triggered star formation creates a cosmic chain reaction that can span millions of years. The first generation of massive stars explodes and triggers nearby gas clouds to form new stars. Some of these second-generation stars are also massive enough to explode as supernovae. They trigger even more star formation in surrounding regions. The result is expanding bubbles of stellar activity that gradually spread star formation across entire galactic neighborhoods. Astronomers observe this cosmic construction process throughout our galaxy today. Many of the youngest, hottest stars in the Milky Way are found near supernova remnants. These are the expanding shells of gas from ancient stellar explosions. These stellar nurseries show clear evidence of triggered star formation. New stellar populations are arranged in patterns that follow the shock fronts from previous explosions. The death of massive stars becomes the catalyst for creating their stellar descendants. Cosmic destruction and construction operate as complementary processes in an ongoing cycle. This cycle has been building galactic complexity for billions of years. Supernovae operate as the universe's most powerful heating systems. They pump enormous amounts of thermal energy into the space between stars. They fundamentally alter how galaxies evolve. Each stellar explosion heats surrounding gas to temperatures of 10 million degrees Celsius. It creates vast bubbles of superheated plasma that can expand across hundreds or thousands of light years. This cosmic heating process transforms the character of entire galactic neighborhoods. Cold interstellar gas that was previously available for star formation gets heated to such extreme temperatures that it expands rapidly. It becomes temporarily unusable for building new stars. Supernovae essentially create galactic heating systems that regulate star formation rates. They do this by controlling the temperature and density of interstellar material. The thermal energy injection operates on truly astronomical scales. Multiple supernova explosions occurring within the same galactic region can create what astronomers call superbubbles. These are cavities of million-degree gas that can grow to sizes of thousands of light years across. These cosmic heating zones contain so much thermal energy that they fundamentally reshape the structure and evolution of entire galactic spiral arms. But this galactic heating serves important evolutionary purposes beyond just warming interstellar space. The hot gas created by supernova explosions drives powerful galactic winds. These winds can actually blow material completely out of smaller galaxies. This process regulates how fast galaxies can grow by limiting the amount of gas available for continued star formation. Supernovae essentially provide cosmic population control for galactic communities. The heating also enriches intergalactic space with heavy elements. It prepares the cosmic environment for future galaxy formation. When supernova-driven winds blow element-rich gas out of galaxies, this material eventually gets incorporated into later generations of galactic systems. The universe's thermostat not only regulates individual galaxy evolution, it also prepares the cosmic environment for building more chemically sophisticated galactic communities. Stellar explosions heat the universe in ways that ultimately benefit cosmic evolution. They distribute heavy elements and regulate star formation rates across cosmic time. Supernovae operate as the universe's most powerful particle accelerators. They launch high-energy cosmic rays that travel across galactic distances. They fundamentally influence biological evolution on Earth. These cosmic ray particles are primarily protons accelerated to near light speed. They carry tremendous amounts of energy and create measurable effects in Earth's atmosphere and biological systems. Supernova shock waves accelerate particles through magnetic field interactions that work like cosmic particle colliders. When charged particles encounter the complex magnetic fields around expanding supernova remnants, they get bounced back and forth repeatedly. They gain energy with each interaction until they reach speeds approaching the velocity of light. These cosmic ray protons carry energies millions of times higher than anything achievable in human-built particle accelerators. When cosmic ray protons slam into Earth's upper atmosphere, they trigger nuclear reactions that create carbon-14. This is a radioactive isotope that becomes incorporated into all living organisms through photosynthesis and the food chain. The cosmic ray production of carbon-14 provides the foundation for radiocarbon dating. This is one of archaeology's most important tools. Without supernova-generated cosmic rays, scientists couldn't determine the ages of ancient artifacts. They couldn't track human civilization's historical development. But cosmic ray interactions with Earth's atmosphere and biosphere go far beyond carbon-14 production. High-energy particles create additional radioactive isotopes. They generate secondary particle showers that reach Earth's surface. These cosmic ray impacts cause low-level radiation exposure that creates genetic mutations in living organisms. These are random DNA changes that provide the raw material for biological evolution. Scientists estimate that cosmic ray radiation contributes roughly 10% of the natural background radiation experienced by life on Earth. This constant, low-level bombardment from ancient supernova explosions creates genetic diversity by inducing mutations at steady rates throughout evolutionary history. The death of massive stars billions of years ago continues influencing biological evolution today through cosmic ray particles. These particles originated in stellar explosions occurring before Earth even existed. Your DNA carries subtle signatures of cosmic ray impacts. They came from supernovae that exploded in distant parts of the galaxy millions of years ago. Without supernova, the universe would remain a sterile collection of hydrogen and helium gas floating in empty space. No carbon-based life forms could exist because carbon nuclei can only be formed inside stellar cores and distributed by explosive stellar death. No rocky planets could form because silicon, iron, and other heavy elements essential for planetary geology require supernova nucleosynthesis and dispersal. The cosmic dependency runs deeper than just elemental abundance. Complex chemistry itself becomes impossible without the heavy elements created by stellar explosions. Water molecules require oxygen atoms forged in massive stellar cores. Organic compounds need carbon and nitrogen from stellar nucleosynthesis. Even the simplest biological molecules depend on elements that can only be created through nuclear processes occurring inside stars. They must be distributed through supernova explosions. Rocky planet formation requires enormous quantities of heavy elements that early universe conditions could never provide. The first billion years of cosmic history contained almost no elements heavier than lithium. Terrestrial planets like Earth could only form after multiple generations of massive stars had lived and died. Their supernova explosions enriched surrounding space with silicon, iron, magnesium, and other rock-forming elements. The timeline of cosmic chemical evolution reveals this fundamental dependency. The first stars formed roughly 200 million years after the Big Bang, but these early stellar giants contained almost no heavy elements. Only after several generations of massive star formation and supernova explosions did the universe change. It developed enough heavy element abundance to support rocky planet formation and complex chemistry. Earth-like worlds could only begin forming roughly 8 billion years after the Big Bang. This creates a profound cosmic connection between stellar death and biological possibility. Every breath you take depends on oxygen atoms forged inside massive stellar cores. Every heartbeat depends on calcium ions created during supernova nucleosynthesis. Every thought depends on phosphorus atoms distributed by ancient stellar explosions. The fundamental chemistry of life requires cosmic recycling through stellar birth, evolution, and explosive death operating across billions of years. Without the universe's most violent stellar explosions, complex chemistry would be impossible. Rocky planets couldn't form, and carbon-based life would never emerge anywhere in the cosmos. Supernova explosions are an essential cosmic prerequisite. They transform a simple hydrogen-helium universe into a cosmos capable of supporting the chemical complexity needed for planets, life, and intelligence. Throughout human history, a select few stellar explosions have earned celebrity status by becoming bright enough to see with naked eyes and dramatic enough to capture in historical records. These cosmic celebrities represent the universe's greatest hits. Stellar explosions so spectacular they transcended astronomical obscurity to become part of human cultural memory. The most famous member of this exclusive club exploded in 10 or 54 AD. It created what Chinese astronomers called a guest star bright enough to see during daylight for 23 days. This stellar explosion, located roughly 6,500 light-years away in the constellation Taurus, created the Crab Nebula, an expanding shell of stellar debris that remains visible today through telescopes. Chinese court astronomers recorded this cosmic visitor with remarkable precision. Modern astronomers can trace the supernova's evolution across nearly 1,000 years of expansion. European astronomers joined the supernova celebrity watch in 1572. Tycho Brahe spotted another new star that blazed brighter than Venus for several months. This stellar explosion challenged the prevailing belief that celestial spheres were unchanging and eternal. Tycho supernova, as it came to be known, helped revolutionize astronomy by proving that the heavens could experience dramatic changes. The cosmic explosion became a catalyst for overthrowing ancient astronomical dogma. Kepler's supernova of 1604 provided the final act in this historical trilogy of naked-eye stellar explosions visible from Europe. Johannes Kepler studied this cosmic firework for over a year. He tracked its brightness changes and noted how it gradually faded from view. His detailed observations helped establish systematic methods for studying transient astronomical phenomena. These three historical supernovae remain the last stellar explosions bright enough to see without optical aid from Earth. Modern space telescopes have democratized supernova discovery. They detect thousands of stellar explosions throughout the observable universe. The Hubble Space Telescope alone has captured images of supernovae exploding in galaxies billions of light-years away. Digital sky surveys now discover dozens of supernovae every month. They've transformed these once rare cosmic celebrities into regular astronomical observations. Yet none of the modern discoveries match the cultural impact of those historical stellar explosions. They were bright enough to surprise ancient civilizations and change the course of astronomical thinking. When Betelgeuse finally explodes as a supernova about 642 light-years from Earth, it will be the most spectacular astronomical event in recorded history. The explosion will reach peak brightness equivalent to a half-moon visible during broad daylight. It will cast shadows at night and remain easily visible for several months. Yet, despite this incredible cosmic light show, the supernova poses minimal direct threat to Earth's atmospheric protection or biological systems. The key to Betelgeuse's safety lies in the inverse square law governing radiation intensity. At 642 light-years distance, even the most energetic supernova radiation gets diluted by enormous factors as it spreads across cosmic distances. The gamma rays and X-rays that would prove lethal at closer distances become manageable increases in background radiation by the time they reach Earth's vicinity. Earth's atmosphere and magnetic field provide additional protection against the Betelgeuse supernova's radiation effects. Our planet's ozone layer effectively absorbs most harmful ultraviolet and X-ray radiation from cosmic sources. The magnetosphere deflects charged particle streams away from Earth's surface. These natural protection systems have successfully shielded our planet from cosmic radiation for billions of years. They will continue operating during the Betelgeuse explosion. Scientific calculations suggest that Betelgeuse's supernova would increase Earth's radiation exposure by roughly 10%. That's comparable to the natural variation in cosmic ray intensity that our planet already experiences due to solar activity cycles. This represents a measurable but not dangerous increase in background radiation levels. The explosion might slightly enhance aurora displays at high latitudes as additional charged particles interact with Earth's magnetic field. The Betelgeuse supernova will provide an unprecedented opportunity for scientific observation rather than a cause for concern about planetary safety. Modern space telescopes, neutrino detectors, and gravitational wave observatories will monitor the explosion across all wavelengths and particle types. Humanity will witness the complete stellar death process in real time with instruments that didn't exist during previous historical supernovae. The cosmic fireworks show will advance astronomical knowledge dramatically while serving as a spectacular reminder of our place in an active, evolving universe. Earth gets front-row seats to cosmic destruction without facing the dangerous consequences of sitting too close to the stage. Commercial airline pilots and flight attendants experience significantly higher cosmic ray exposure than ground-based workers. This happens due to their regular travel through the upper atmosphere, where Earth's atmospheric shielding becomes much thinner. These aviation professionals essentially work in a cosmic ray shower created by ancient supernova explosions occurring throughout galactic history. They accumulate radiation doses that sometimes exceed those received by nuclear power plant workers. At aircraft cruising altitudes, between 35,000 and 42,000 feet, atmospheric protection drops to roughly 1/10 of the shielding available at sea level. Cosmic ray particles that would normally get absorbed by the full thickness of Earth's atmosphere can penetrate to these high altitudes with much greater intensity. Flight crews on polar routes receive even higher doses because Earth's magnetic field provides less protection at high latitudes. The numbers reveal the scope of occupational cosmic ray exposure in modern aviation. Flight attendants on international routes can accumulate substantial lifetime radiation doses. They can approach those of medical workers who regularly operate X-ray equipment. Pilots flying transpolar routes between North America and Asia receive some of the highest occupational radiation exposures of any civilian profession. These cosmic ray doses come directly from high-energy particles accelerated by supernova shock waves millions of years ago. Astronauts face even more extreme cosmic ray exposure during missions beyond Earth's protective magnetosphere. International Space Station crew members experience radiation levels roughly 10 times higher than commercial airline workers. This happens due to their complete exposure to unfiltered cosmic radiation. Deep space missions to Mars or the outer solar system would push exposure much higher. Those doses can approach the limits of acceptable health risks for space workers. Current space radiation safety protocols attempt to limit astronaut career exposure to levels that increase cancer risk by no more than 3%. This means that cosmic rays from ancient supernova explosions directly influence how long astronauts can safely work in space. They determine which missions astronauts can undertake during their careers. The death of massive stars billions of years ago continues affecting human space exploration through persistent cosmic ray backgrounds that permeate throughout the galaxy. Every spacewalk and every high-altitude flight exposes humans to the lingering radiation signatures of stellar explosions that occurred before Earth even existed. Your smartphone contains a cosmic treasure trove of elements. They could only be created through supernova explosions and neutron star mergers billions of years ago. The rare earth elements in touchscreens, camera sensors, and processors required violent stellar deaths. Those events forged their complex atomic nuclei. They needed to be scattered across space for eventual incorporation into planetary materials. Neodymium is essential for smartphone speakers and vibration motors. It forms mainly during neutron star collisions, which can outproduce ordinary supernovae for rare earth elements. The europium that creates red phosphors in smartphone displays requires neutron capture processes. These conditions are so extreme they can only occur during cosmic explosions involving stellar remnants. Your device's rare earth magnet technology depends directly on elements forged in cosmic violence occurring across galactic distances and cosmic time. Medical isotopes used in diagnostic imaging and cancer treatment represent another category of cosmic gifts delivered through stellar explosions. Technetium-99m, the most widely used medical radioisotope for diagnostic scans, doesn't occur naturally on Earth. It must be artificially created in nuclear reactors using principles learned from studying supernova nucleosynthesis. The medical techniques that save lives every day in hospitals operate using nuclear physics discovered through astronomical observations of stellar explosions. Radioactive isotopes used in targeted cancer therapies often mimic the nuclear processes that occur during supernovae and neutron star mergers. Iodine-131 therapy for thyroid cancer employs the same beta decay processes that power supernova light curves. Cobalt-60 radiation therapy uses gamma rays produced through nuclear reactions similar to those occurring in stellar explosion environments. Modern nuclear medicine essentially applies cosmic-scale nuclear physics to human health problems. The platinum group elements are essential for catalytic converters, medical implants, and industrial catalysts. They require cosmic alchemy at extreme conditions found only during stellar explosions. Platinum, palladium, rhodium, and iridium form through neutron capture processes. Those conditions occur when massive stars explode or neutron stars collide. The precious metals that enable clean automotive technology and biocompatible medical devices are literally forged in cosmic furnaces operating at temperatures of billions of degrees. Every advanced technology in modern civilization depends on cosmic recycling through stellar birth, evolution, and explosive death operating across billions of years. The elements in your pocket represent atomic nuclei assembled in stellar cores. They were scattered by supernova shock waves, concentrated through planetary formation, and refined through geological processes into the materials that enable 21st century technology. You carry the products of cosmic violence in your daily life. They've been transformed into tools that extend human capability and improve quality of life. This took billions of years of stellar evolution and galactic chemical enrichment.